Okay, so we're going to be looking at identify basic facts about the principles, capabilities, limitations of line of sight microwave radio system. 5 Foxtrot. Remember, you got to have 70% on the KPC. I will tell you that this is module 11. They're going to get into the nitty gritty as well as the equipment with it. AFSC application, oh yeah, you're going to be using this, especially here in the course for line of sight microwave systems. This is how cell phones and the military get from point A to point B, especially when you hit a cell tower, goes down into that little central office and might get retransmitted as a microwave signal to the distant end. It also relies on that in how we get when they hand you off to another cell site. Excuse me. So what is the overview? Well, microwave line of sight radio systems. We have used this in the past. We're still using it. We've upgraded from what is called the GRC 239, better known as a TISR, up to what is called the P2P point-to-point system. The difference between the two is the Jerk 239 could only go up to 25 miles, where the P2P can go up to 120 miles. It's pretty far. Uses pretty much the same frequency area in the, I think the 3 to 5 gig for the P2P and 14.4 to 15.25 gig for the TISR. So they are considered microwave line of sight systems. There are 4 different types of basic repeaters out there, and we also talk about the limitations of those repeaters, because when you're dealing with line of sight microwave systems, there is repeater systems for that, i.e. going from, if you're in the middle of nowhere, you're going to have those repeaters in between cell sites. It does use a tropo in order to get from point A to point B, better known as fraction. Scatter volume and common volume is another point to it. We do look at something called blurring. It is cheaper than satellites. We're talking medium distance. There is a place in your study guide workbook that I pulled out of the internet to show you some of those repeater systems. They sometimes cover, several hundred miles. We're going to be looking at in antenna terms and also tropospheric antennas. Let's take a look at the microwave radio system. This is considered a true line of sight because most of your microwave systems, actually all that I know of, transmit a unidirectional signal, and it is considered true line of sight because there is no physical obstacles between the transmitting antenna and the receiver. Because if there is, you don't make comm. That's the problem. Something gets in between it, you're going to have an interruption of your service. When they say multi-channel wideband communication, they're talking about digital information being transmitted on a carrier. In your study guide workbook, there is this, this setup, a diagram, and on this diagram, let me grab an arrow. We have true horizon, we have optical horizon, and then we have radio horizon. It's identified between the true and optical is 18%, and between optical and radio is 15%. Now, when you look at true horizon versus radio horizon, you get 33%. They're doing it by percentages because it depends on what is actually happening in the atmosphere as to how far they will go. It's just like the ionosphere. So when You go from night to day, the exciting of the ion atoms in the atmosphere will determine how the D, E, and F later react, and they have a tendency to expand and contract during that time frame. Same with your radio horizon and what it's going to do out there. You've got some things called temperature inversion, which can affect radio signals, sometimes really good as far as distance and sometimes really bad as far as even communication. When we look at what the repeaters are and what they do for us, the idea behind them is when I need to go further, I put a repeater in. Why? Because my equipment can only go so far when you got from radio to radio, but when you add a repeater in there, you can extend the distance. The whole idea behind the transmitter and receiver for this is you got a couple different things that happens. You have frequency translation and amplification that happens. Without those two items, your repeater does not work. Let's take a look at each one of them individually. The idea behind frequency translation is we're taking the receive frequency, it's at 1. When you retransmit it, it doesn't make any sense to retransmit it as the same frequency as you received it. Why? It's going to interfere. So there is that frequency translations where you flip it to another frequency. Normally it's about 200 megahertz at a minimum to retransmit it as a different frequency. So let's just say that you're at 100 megahertz, your retransmission, that's what your receive frequency is. You would literally have to put it at 200 megahertz above 100, so that's 300 megahertz. So receive it on 100, retransmit it at 200. For amplification purposes, you're receiving it and it's going to be extremely weak. Remember path loss, free space loss and that. When you transmit out 10 watts, depending on the distance, you might only get 100 milliwatts. So you got to reamplify it. So you're going to bring it in, clean it up, and resend it out at a stronger signal so you can get it to the end. For repeaters, there are 4 different types. We have the RF repeater. This is the most simplest one. The problem is with the RF repeater is because you're taking the frequency and just recombining it with a different frequency to have that frequency translation, you end up with a lot of noise on it. It is desirable as far as cheaper solutions, but it's not always a good thing. When you get to the IF repeater breaks that RF signal down from the original frequency down to what's called an IF. That's a intermediate frequency. And what happens is when it gets to that intermediate frequency, then you're able to clean it up and then be able to boost it back up to a different frequency, which is a frequency translation for it to be amplified. And it doesn't have as much noise on it. The idea behind when you break these repeaters down into more signals, in other words, you go from an RF to the IF to what we call a baseband signal and then to the actual original signal. Every time you break it down further, you get to clean it up and there's not as much noise on it when you have to retransmit it. So the IF repeater is the start of it. When we look at the baseband repeater, that one breaks it down into the digital stream. In other words, the aggregate. And you can do a couple different things with this. It makes it easier to clean up all that noise. And 2 is you could drop another set of information in there. Depends if you got it running to a multiplexer or not. It could be classified as a hub. If not, break it down to the baseband signal and send it out. Cleans it up. But the best repeater that's out there, and of course, money talks, So it's going to cost a lot of money to break it down even farther to the original signal. So you go from RF to IF, baseband, and let's just say it's VoIP. Now it's down to the original analog signal. Again, really expensive because of the equipment that has to go in between it for it to retransmit. But it's a lot easier to send it back out, and you can have multiple repeaters compared to like the RF or the IF repeater. We only touch upon the RF repeater and what is called PDM. So you have FDM, which is the RF, and PDM, which is actually the baseband. There is a difference between those two, is how many repeaters you can use without the noise becoming a factor. I think RF is like 8, and the baseband, which PDM, you can break it down into 15. So what are some limitations of the repeaters? Well, what is the distance that I need to cover? All right, a radio to radio may not cover it. You put a repeater in there, you extend the distance. But when you look at how many repeaters you might have to use, it may not come into play where it is monetarily feasible to do that. What's the effective range of your equipment? Obviously, the tisser that the P2P is replacing, going from 25 miles to 120, there's a pretty good obvious reason why you would want to use the P2P over the tisser when we're looking at the effective range of the equipment. We also got to look at the terrain. What is in between us? Okay, the terrain is a big thing when it comes to if it's flatland versus mountainous land versus hills and so forth and so on. Obviously, you would want the repeaters in an area where you can retransmit and get the furthest distance. But then again, what is it you're trying to do? Are you looking at microwave line of sight? Obviously. So what do you need to do in order for that to happen? So let's take a look at the need to drop or insert signals along the way. Again, there's that FDM versus TDM. FDM has a lot of noise in it. TDM, by the time you break it down even into more repeaters, you're probably going to have is less distortion versus the FDM noise. Next up, we're going to be looking at the Tropo. What the heck are we doing with the Tropo? Well, Tropo is the closest in what we're in right now. You got the ionosphere that stretches from the Tropo all the way up. But those are the two spheres that we like to explain that we use for radio communications. But the Tropo, since it's so close to us, we use a lot of the line of sight, handheld radios, mobile radios, things that can go from short distance to medium distance. And then we use the HF for long haul. The Tropo does have an area in it where you can refract some of the signals back down to Earth. Normally, if you take a look out on the internet, you will see somewhere between 144 megahertz all the way up to 10 gigahertz. That's about the limit on that. Now, I have seen some websites where it even goes down as low as 50 megahertz, but they say that that's kind of sketchy because that's a hit and a miss. But your range between 144 to 10 gig is pretty much consistent. Again, has a lot to do with what's happening in the Tropo at that time. This Tropo Scatter circuit, you'll notice that going from Okinawa to the Philippines to a couple of the other islands there, these are pretty good long shot or over the horizon, you know, looking at 800, 900 miles between them. And the reason why you can get a longer shot on this is because it's over the ocean. That's the reason why you can use it, because it's basically at the horizon and trying to get it just over the horizon. You don't have a whole lot to block you, as opposed to if you were on a continent and having to worry about hills, mountains, trees, cities, things like that. When we look at that refraction point, there's a couple names that we give it. First of all, it's called the common volume or the scatter volume. This is where that little area has the place where it will get refracted back down to Earth. Most of it's going to keep traveling through to space. So it's just a very small portion, and you have to have a very good gain antenna on it. It's the reason why we use the parabolic dish with a good waveguide in. We have something called blurring. Now, blurring is when you have some problems with your frequencies, your polarization, things like that. The idea behind this is to make sure that you have clear communication and nothing is interfering with it. So we have 4 items that helps us with overcoming this blurring. The big thing here is polarization. Now, I've worked with the TISR, and one of the things that they have you do is one end is vertically polarized, the other end is horizontally polarized. And you're going, well, how are they receiving? Well, there is a twist on that waveguide to where it doesn't matter if it's vertical or horizontal, it will be able to receive it. And I explained to you that when you slant an antenna at 45 degrees, it becomes both vertically and horizontally polarized. Well, if you got one antenna that's horizontal, the other antenna, horizontal and the other vertical antenna, and they have different frequencies, they have a tendency not to interfere with each other, especially when you're looking at 200 megahertz apart in 2 different type of linear polarizations. You can also, and I like to combine polarization with frequency with that aspect. Another 2 that I also like to link together is angle and phase. Angle, because you got to figure out where in that tropo that you're going to get the best refraction. The angle on one end is probably going to be very different than the angle on the distant end that you're trying to reach. You might be at different heights. You might have to look at where one might have to have a steeper angle than the other one, but as long as both can communicate, shouldn't be too much of an issue. But there will be differences between the 2. And then the space. When we were doing the TISR back in the day, back last year, you could set up the TISR. Now, let me explain line of sight. You need to be aimed at each other's antenna. Au contraire, as an experiment, and I tried this, in the classroom, I could point the antennas this way, and they would still talk to each other. Go outside, point the antennas both different directions. It would still work. Still communicate. Why? Because the space between them was too short. So you need to be at a distance for these things to work properly. In other words, they were saturating what I call the receive end, and it didn't matter where you pointed them, it was really strong at that point. So the farther you get it away, the better results that you will have. Not to mention that when you're only 100 feet apart, I think it's the north side of Jones Hall is where we would set up, and we would get a little bit of blowback from the hangars that were over there. Sometimes they would interfere with them. So you get something like that, as opposed to if you were, let's say, 20 miles to 100 miles apart, you're not going to have that issue with space, because the transmitting and receive antennas are very sensitive, And that was the reason why we were having problems all the time with them. Especially if you did it in the hallway. Hallway acted like a waveguide, and sometimes the receive end on both of them would get saturated and we'd have problems with it. Tropo Scatter does require powerful transmitters, but because we have a waveguide on them and can point them and with high gain antennas, we don't have to have like 1,000 watts on them. In the case of the Tropo, you're looking at somewhere between milliwatts to watts, depending on what you need to transmit for. I think the P2P, you can change the wattage on them through the computer, i.e. it's a software-defined radio when you think about it. You do need to have sensitive receivers, and that's the reason why when you're so close to each other, you do have sensitive receivers, and it creates problems if the signal is too powerful. We don't have the capability in the tisters to turn it down. We do with the P2P. And I like that high gain antennas. That's basically how big is the dish. The whole idea behind Tropo is you're dealing with a lot of data that's being transmitted through it. It is a cost-effective system when you compare it to satellites. Satellites are in the billions of dollars as opposed to Tropo, which is in hundreds of thousands of dollars for a system. With the P2P, I think they were about $2,000 each. Antenna terms, you've seen some of these before, but we do use them in here. You got reciprocity. Just remember, it's if an antenna can transmit well, it should be able to receive well. Directivity and gain. The better that you have directivity, you can improve your gain with it. Like I compared the omnidirectional antenna to a bidirectional antenna. Well, then it does have gain at that point. When you compare a bidirectional antenna to a unidirectional antenna, you got gain, but you got to compare it to it. Also, the bigger the dish, the more gain that you're going to have. Doesn't equate to the antenna. Because remember now, I told you that we're going to be in the gigahertz. That antenna is going to be pretty small. We also look at polarization. Remember, the E fields is what determines it. Linear versus non-linear. Remember, you can talk between the two. You can't talk between two linear antennas that are opposite. In other words, a vertical to a horizontal. Frequency. Always remember that every time you change frequency, you're changing the wavelength. Frequency and wavelength are inversely proportional. Higher the frequency, the smaller the wavelength. Bandwidth. Of course, it could be multiple things. This one is looking at the range of frequencies that the equipment can transmit. You can relate that to what is the data that you're doing. We have tropospheric antennas. This is a horn antenna. It is the most simplest. Again, impedance matching. That has to do everything with its weight. You got a parabolic. This is one of those antennas where it's very directional. Antenna size and gain are directly proportional. Yeah, that's kind of crazy. The bigger the dish, the more gain that you're going to have. Antenna size has everything to do with frequency. You can have a front feed or a rear feed. Front feeds are okay. Rear feeds are the best. We have two of them. One's called a Cassegrainian. The other one is a Cutler. Cassegrainian has something called a sub-hyperbolic reflector on it, and the Cutler has what I call two fins that are in the opposite direction of what a hyperbolic sub-reflector would. Tropo Scatter, misspelled. I just now realized that. Everybody see it?
Isn't that a repeat slide?
Wouldn't doubt it. It does look like it's a repeat. Looks like where was that? Back here.
Yes, sir.
See, that one spelled right. Wow. This. Okay, so we have microwave LOS systems. Remember, line of sight, meaning true line of sight. There are four basic repeaters. You have the RF, IF, baseband, and audio. The limitations of the repeaters has everything to do with their equipment and terrain and things like that. And then, of course, you have tropo and scatter volume and common volume. Any questions on that?
This was Foxtrot, what we just learned?
This is Foxtrot.
That wasn't as bad as I thought it was going to be.
Yeah, it was made out to be horrible, but it was a lot, but not too bad.
Yeah,
Yes.
when you get into the information, it's a little bit more explanatory. And again, if you have questions on it, I do not have a problem with answering them. You teach this part of Block 7 in it. Loved it. Again, I love the antenna portions as well as the computer side, which is that multiplexing and